We've sent humans to the moon. We've drilled tunnels beneath entire oceans. We've built towers that scrape the very edge of the clouds. But here's a question that has quietly humbled every engineer who has seriously tried to answer it. Could we build the Great Pyramid of Giza today from scratch? With all of our modern technology, our billion-dollar machinery, and our AI-powered logistics. 2.3 million stone blocks, some weighing 80 tons, a total weight 12 times heavier than the Burj Khalifa. Today, we're breaking it all down. Real costs, real engineering, and a number at the end of this video that will genuinely surprise you. Before we talk money and machines, let's understand the scale of what the ancient Egyptians actually built, because the numbers are almost unbelievable. The Great Pyramid of Giza stands 481 feet tall. That's a 40-story building. It covers 13 acres at its base. That's roughly 10 football fields laid side by side. Inside this structure, there are 2.3 million individual blocks. The lightest ones weigh around 2.5 tons each, heavier than a full-size pickup truck. The heaviest granite slabs inside the king's chamber, some of those push 80 tons. That's the weight of a fully loaded Boeing 737. And there are 2.3 million of these blocks. Here's the detail that genuinely stops engineers cold. The 4 base corners of this pyramid differ in length by less than 2 inches. The entire 13-acre base is level to within just 0.8 inches. That precision, achieved 4,500 years ago, is extraordinary, even by today's standards, achieved without lasers, without GPS, without computers. The total weight of this structure is 6 million metric tons. The Burj Khalifa, the world's tallest building, weighs 500,000 metric tons. The Great Pyramid is 12 times heavier. So, now you know what we're dealing with. Let's talk about what it would actually take to build it. Starting with the ground beneath our feet. Phase 1 is something most people never think about. But it's where a project this size can fail before a single stone is placed. You can't just pick any piece of land. You need bedrock, solid, stable, geological bedrock, capable of holding 6 million metric tons without shifting a single millimeter. This isn't just theory. Look at the bent pyramid in Dashur, built by Pharaoh Sneferu, Khufu's own father. Partway through construction, engineers realized the ground assessment was wrong. The pyramid began to destabilize, and they had to change the angle mid-build to save it. Even 4,500 years ago, bad ground meant a bent pyramid. Today, we'd use ground-penetrating radar and seismic sensors to scan 200 feet deep before breaking ground. Then GPS-guided bulldozers and laser leveling to flatten 13 acres to within 1 millimeter of perfect level. Because at 481 feet of height, even a small error at the base becomes a visible lean at the top. We'd pour a reinforced concrete mat foundation, 13 feet thick, across the entire 13-acre site. That's 500,000 metric tons of concrete and steel. Phase 1 total cost alone, $550 million. And we haven't placed a single pyramid stone yet. Now we face the most staggering challenge of the entire project. Cutting 2.3 million blocks of stone to precise rectangular dimensions. And the clock starts the moment we break ground. The limestone came from the Tura quarries, just south of Cairo. The granite for the King's Chamber came from Aswan, 560 miles away. The ancient Egyptians used the Nile River to float massive barges, and we know exactly how they did it because of a papyrus diary discovered in 2013, the oldest papyrus ever found, written by a foreman named Merer, who recorded his crew's daily work ferrying limestone blocks from Tura to Giza, a 4,500-year-old shipping manifest written in real time. The most advanced stone-cutting technology available today is the diamond wire saw. One machine can produce around 100 large blocks per day. Sounds impressive until you do the math. 100 blocks per day, 2.3 million blocks needed. That gives us 63 years. So we don't use one machine, we use 250 diamond wire saws, running simultaneously 24 hours a day, right at the quarry face. Each machine draws 80 kilowatts of power. 250 machines running non-stop means a 20 megawatt continuous power demand. That's roughly the daily electricity consumption of a small American city. 5 years of that power bill alone? $155 million. High-quality limestone runs $120 per metric ton. The granite for the King's Chamber is significantly more expensive. Total raw stone material cost for the entire pyramid? Approximately $1 billion. To put that in perspective, the entire Burj Khalifa construction cost $1.5 billion. We're spending 2/3 of that just on raw stone. Phase 2 total, $1.3 billion. The stone is cut. It's sitting at 2 quarries, 560 miles away. Now we have to move it, and this is where it gets truly insane. Getting 6 million metric tons of stone from 2 quarries to the construction site is one of the largest peacetime civilian transportation operations in human history. The ancient Egyptians had a secret weapon, the Nile River, and we know exactly how they used it because of the diary of Merer, the oldest papyrus ever discovered, found in 2013 by archaeologist Pierre Tellet. Merer wrote daily logs of his crew, ferrying limestone blocks by barge from Tura to Giza, a 4,500-year-old shipping manifest written in real time. Today, we cannot use the Nile the same way, which means we go back to trucks, hundreds of them. A standard heavy-duty flatbed truck can haul 30 metric tons. To move 6 million metric tons over 5 years, we need approximately 110 fully loaded truck arrivals at the construction site every single day. Every 13 minutes, another truck arrives. Around the clock, every single day, for 5 years. The Aswan to Giza route is 560 miles of Egyptian highway, coordinating hundreds of trucks, fuel depots, maintenance crews, rest stations, and police escorts. across 560 miles of desert highway every single day for 5 years is a logistics operation that rivals military supply chains. This never stops. Transportation phase total, $200 million, which brings our running total to approximately $2 billion. And we still haven't lifted a single block into position. The stone is on site. The foundation is ready. Now comes the part that has genuinely stumped modern engineers: the construction itself. This is where modern engineering meets its most humbling opponent. Not weather, not politics, not budget. The opponent is physics itself, and a 4,500-year-old structure that somehow already won that fight. Modern tower cranes are extraordinary machines, but they operate under an unbreakable law of physics. The larger the crane's operating radius, the less weight it can safely lift. And the real challenge here isn't lift capacity, it's positioning. As the pyramid rises and narrows, the working surface at the top keeps shrinking. No single crane, anchored to the outside edge, can reach every point of an ever-changing working surface. No single solution exists, so we build a network. We deploy 10 of the most powerful specialized tower cranes in the world, positioned at precisely calculated intervals around the pyramid perimeter. Each crane handles its designated zone. But here is the engineering challenge within the engineering challenge. As the pyramid rises, every crane must be dismantled, lifted higher, and re-anchored to the growing structure. At 210 courses of stone, that repositioning happens dozens of times per crane. 10 cranes, 0 downtime. Every single one of the 2.3 million blocks must be placed with millimeter accuracy. The joints between blocks are so tight that a credit card cannot slide between them. Achieving that tolerance while dangling a stone the size of an SUV from a crane cable at heights up to 481 feet in desert wind conditions is one of the most demanding precision operations ever attempted. 2,299,999 blocks to go. This project demands 3,000 skilled workers on site simultaneously, not laborers, specialists, structural engineers, crane operators, certified for extreme loads, precision stone masons, laser survey technicians. Every one of them working 12-hour rotating shifts around the clock for 5 years. Their combined wages, housing, food, medical care, and safety insurance? $400 million. The ancient Egyptian workers received food, housing, medical care, and wages. So do ours. 4,500 years, same basic contract. Phase 4 construction total, $800 million. Running total now, $2.85 billion. 8 years of work, the structure stands. But if you had seen the original pyramid, you would not recognize what we have built. Because what you see at Giza today is not what the ancient Egyptians built. What they built was something far more extraordinary. One final phase remains. Here is something that genuinely shocks most people when they hear it for the first time. The pyramid you see standing at Giza today, the rough, stepped, gray limestone structure, that has become one of the most photographed landmarks on Earth, is not what the ancient Egyptians built. This is what was built. Every single casing stone gone. A handful of the original casing stones still survive at the base of the pyramid, and they tell us everything we need to know about what was lost. Run your hand across one, and you feel a surface so perfectly flat and so smooth it could have been cut yesterday. The precision of the fit between adjacent stones is extraordinary. Joints tighter than a human hair. This is what 115,000 of them looked like, covering every inch of all four faces. Each casing stone must be cut to a surface flatness tolerance of less than 0.05 inches. That is the kind of precision used in aerospace component manufacturing, applied to blocks the size of dining tables. Using modern CNC stone finishing machines and laser flatness verification systems, we can achieve this. But it takes time, and time costs money. $2,174 per stone. 115,000 stones. $250 million. Installing 115,000 casing stones onto a standing pyramid structure is a different engineering challenge entirely. Each stone must slot into its precise position against already placed adjacent stones, fitting so tightly that mortar is almost unnecessary. Working upward from the base, teams of specialist masons guide each stone into position using hydraulic micro-adjustment rigs, making sub-millimeter corrections until the fit is perfect. Then, the next stone, for 2 years. The final casing stone locks into place beside the capstone at the apex. The pyramid is complete. For the first time in approximately 700 years, it looks as Pharaoh Khufu intended. In the midday desert sun, ancient accounts describe a structure of extraordinary brightness, visible from great distances, a beacon of human achievement, burning white against the desert sky. Phase 5, casing stone total, $250 million. And with that, our pyramid is finished. 5 phases. 8 years of continuous construction. A workforce of thousands. Equipment pulled from every corner of the modern engineering world. Stone quarried from 2 locations, spanning 560 miles. And a foundation strong enough to hold this structure for another 4,500 years. Everything has led to this single number. Let's add it all up one final time. Phase 1, site selection, ground surveys, and the reinforced concrete foundation. $550 million. Phase 2, quarrying equipment, raw stone materials, and 5 years of industrial electricity. $1.3 billion. Phase 3, transportation across 560 miles of desert highway. $200 million. Phase 4, 10 specialized cranes, 3,000 skilled workers, 5 years of round-the-clock construction. $800 million. Phase 5, 115,000 optically polished casing stones, $250 million. The grand total. Conservative estimate. To build the Great Pyramid of Giza from scratch in 2026, $3.1 billion. $3,100 million. 8 years minimum. 3,000 skilled workers. 2.3 million stone blocks. $3.1 billion is almost exactly what it cost to build Palm Jumeirah Island in Dubai. It is roughly what Apple spends on research and development every 38 days. And it is just over twice what the entire Burj Khalifa cost to build, the world's tallest building, which at least has commercial tenants generating revenue. Our pyramid has none. The ancient Egyptians did not build the pyramid because they had better technology. They built it because an entire civilization, every resource, every skilled worker, every supply chain was unified behind a single generational purpose. The pyramid was not a construction project. It was the physical expression of a civilization's complete belief system. That is what $3.1 billion cannot buy. And that is why, despite everything modern engineering can do, the Great Pyramid of Giza remains, in the truest sense, irreplaceable. At the beginning of this video, we asked one question. Could we build the Great Pyramid today? After 8 years of construction, after 3,000 skilled workers, after 2.3 million stone blocks, after $3.1 billion, the answer is, technically, yes. But the more honest answer, the answer that the numbers and the engineering and the history all point toward, is that we would never truly build it. Because we would never truly want to, badly enough. Every great civilization leaves behind one structure that defines what it believed in. Ancient Egypt left the pyramids. Ancient Greece left the Parthenon. Medieval Europe left the Gothic cathedrals. The builders of Cologne Cathedral began in 1248 and finished in 1880. 632 years later, they built for something beyond themselves, for something they would never personally see completed. They built anyway. When was the last time any civilization built for a purpose that large? Before we go, 4 facts about the Great Pyramid that most people never know. 1. The temperature inside the king's chamber stays at a constant 68 degrees Fahrenheit year-round, regardless of outside desert temperatures that can reach 110 degrees. 2. The Great Pyramid was the tallest man-made structure on Earth for over 1,200 years, until Lincoln Cathedral in England was completed in 1311. 3. The mortar used between pyramid blocks has never been fully replicated by modern science. We know its basic composition. We cannot recreate its exact binding properties. 4. The pyramid's 4 sides align with true north, south, east, and west to within a fraction of a degree, an alignment that required an understanding of the stars that we are still studying today. Now here is the question I want you to think about and drop in the comments below. If you had $3.1 billion and the complete engineering resources of the modern world, what would you build? Not what is practical, not what generates revenue. What would you build that 4,500 years from now, people would look at and feel the same awe that we feel standing at the base of the Great Pyramid today? I will read every single answer. The best ones I will feature in a dedicated response video. I genuinely want to know which one surprised you most. If you are not subscribed yet, this is the moment. Because our next video answers a question just as fascinating as this one. What if we tried to rebuild the Colosseum of ancient Rome today with modern technology and a modern budget? The engineering challenges are completely different. The cost is completely different. And there is one aspect of the Colosseum's construction that is so historically significant, so morally complex, that it changes how you see the entire ancient world. That video is already in production. Subscribe so you don't miss it. I will see you there.